Hey people, let's start learning for earning.
Look closely at the physical reality of advanced manufacturing. On one side, we create parts by tearing material away, shearing solid metal into flakes. On the other, we build it up from dust, depositing glowing beads of molten alloy. We are going to dissect the operational mechanics, the hardware architectures, and the strict physical limitations of modern digital fabrication. Both of these methods rely entirely on computerized numerical control, or CNC. This is the programmable automation of physical processes using abstract numbers, letters, and symbols. For decades, the subtractive method dominated the industrial sector. Machines translated digital CAD data into spatial reality by carving it out of a block. Today, 3D printing applies the exact same digital logic in reverse, adding material layer by layer rather than cutting it away. Despite their completely different physical outcomes, both technologies are bound by the exact same constraints. They both require multi-axis spatial positioning and hyper-accurate, closed-loop motion control to function. Let's establish the baseline with the subtractive method. This is the process of removing material from a solid blank, usually metal or plastic, using high-speed rotating cutting tools. This diagram details the basic architecture of a 3-axis CNC mill. Notice the rigid relationship between the spindle above and the workpiece. The machine dictates movement strictly along a rectangular coordinate system, navigating the physical boundaries of the X, Y, and Z axes. A computer translates sweeping digital curves into thousands of microscopic linear steps. These are output as G and M codes, which explicitly tell the motors where to go and how fast to get there. Achieving sub-millimeter precision requires mapping a perfect digital coordinate system onto heavy, vibrating physical hardware. But there is a massive engineering hurdle in doing this. A computer telling a motor to move to a specific coordinate does not guarantee the motor actually reached that exact position. Look at the top half of this schematic. This shows an open-loop control system. It relies entirely on stepper motors and pulse train inputs to execute movement commands blindly. If the cutting tool skips a mechanical step, the system has no way of knowing it is out of alignment, and it will continue cutting a flawed part. High-precision machines solve this by using a closed-loop architecture with servo motors and digital-to-analog converters. An optical encoder physically attached to the lead screw reads the actual physical position of the table. It sends a feedback signal back to a comparator, which instantly calculates and corrects any positional errors in real time. Because of this self-correcting ability, closed-loop systems currently dominate 80% of the industrial market, particularly in high-stakes fields like EV battery assembly. True industrial precision is not achieved by flawless initial execution. It is achieved by continuous, high-speed error correction. Even with perfect error correction, a 3-axis machine runs into a severe physical limitation: tool access. The spindle can only cut what it can physically reach from straight above. If an engineer designs an internal channel or a deep undercut, the rigid shaft of the cutting tool will physically collide with the outer wall of the workpiece before the tip can reach its target. The hardware solution is the rotary 4th axis, pictured here on a Haas unit. Instead of trying to maneuver the tool around an obstacle, the machine mounts to that chuck and rotates the workpiece itself. Moving to 4 and 5-axis machining allows continuous rotation around the X and Y axes. This makes complex, aerospace-grade contours achievable without an operator ever stopping to reposition the metal. Coordinating 5 axes simultaneously requires serious processing power. The controller uses complex mathematical matrices, known as kinematics, to constantly calculate the exact required angle of the tool relative to a part that is spinning through 3-dimensional space. Multi-axis machining overcomes physical tool access limits by turning a stubborn geometrical puzzle into a highly complex, solvable math problem. That exact same 5-axis kinematic code used to drive a subtractive cutting tool can be repurposed to drive an additive deposition nozzle. This is the operational basis of directed energy deposition, or DED, an additive process that builds structural metal components layer by layer. The physics of DED are extreme. A high-power laser generates a localized molten pool on the surface of the part, while a continuous stream of transport gas injects metallic powder directly into the melt. That transport medium is usually argon gas, which also serves as a shielding agent to prevent the molten metal from oxidizing in the surrounding air. Because the tool head is depositing material outward rather than cutting inward, the internal geometry limitations of subtractive manufacturing disappear completely. This enables the greatest advantage of DED, the ability to execute multi-material printing on the fly simply by changing the powder mix feeding the nozzle. An engineer can program a part to possess higher thermal conductivity at its base, gradually transition the alloy ratio as it builds, and achieve extreme mechanical hardness at the tip, all within a single continuous print. Subtractive manufacturing is limited to the uniform properties of the raw starting block. Additive manufacturing allows us to engineer the exact molecular properties of the material itself during the eld. Both methods have stark physical trade-offs. While additive solves complex geometric and material constraints, it struggles to match the raw production speed and smooth surface finishes of traditional milling. For high-volume production, extreme dimensional accuracy, and strict repeatability, CNC machining remains the undisputed industrial standard. Look at these Kepler electronic enclosures. In custom aerospace or complex electronics applications, dimensional precision is an absolute requirement. Creating these sweeping internal tracks requires uncompromising machine stiffness and the highly tuned accuracy of a closed-loop system. Whether a factory chooses to cut material away with an end mill or build it up with a laser, the success of the entire operation relies on the industrial motion controller. These specialized controllers act as the brain of the machine. They manage precise position, rotational velocity, and applied torque across dozens of axes simultaneously. The modern market for these brains is splitting. Engineers now choose between standalone hardware designed for absolute deterministic speed or PC-based controllers that leverage standard operating systems for complex algorithmic processing. Driven by Industry 4.0 trends, the latest controllers are integrating AI-enhanced autonomy and predictive digital twins directly into the machine's logic. Ultimately, the intelligence of the invisible control loop orchestrating the dance determines the limits of modern production, a computational reality that governs the hardware regardless of whether it's adding or removing material.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.